Welcome back after a nice slaughtering session on Friday. Let me dive right into it. That's the score chart from last Friday. The mean was 56.2 standard deviation, which is basically a measure of the spread around the mean, was 18.6, which means that this exam really pulled a lot of performances away from each other. Okay? So it's a very broad distribution. For a teacher, this is great, because I can beautifully see a spectrum of performances. For the student, this of course is not nice. You all want to be right kind of close together and maybe somewhere more towards the 99. So you may feel that 56 is not so good. Actually, it's completely fine and completely on target. Last year, the performance was only one percentage point higher, so it was 57. Now it's 56, so that's very much average, I would say, from year to year. So this is not anything out of the ordinary. Let me say a few things. The exam was, like I said before we started, it was a little bit tight. This is part and parcel of having only 50 minutes, including arranging things, getting other class out, new class in, taking your seat, distributing the exam. You cannot do it in another way. You cannot put the exam on the seat beforehand because it is allocated seating. You don't have 600 copies to fill all the chairs. You simply cannot do that. So we have to do it in the way we did it. It takes a little time, takes a couple of minutes off your examination time, and you know that, okay? Many people told me that, and I said, well, I know that, okay? And this is, again, part of this exam. This exam was tight, it was not very pleasant and comfortable, but on the other hand, we still get a very good impression of what the performance of this class is, okay? The second midterm, you will see, will go a lot better. It is a little less intense, and you will feel more comfortable. And the final will be relatively, I would say, not easy, but more time for you to think through the questions. This midterm also kind of like sets the stage, because there are a couple of topics here that are important for you to be able to do these questions quickly. And so that's why this exam has a lot of stuff in it. It's trying to test you on several things, you squeeze it all in, and this is the result. So not bad at all. We are on target. If you are on the low side of the mean, take this exam as an opportunity to see what parts of the material need to be improved on. Okay? So what is your personal weakness on the exam that needs extra attention? You can come to office hours. You can speak to your tutors, the discussion leaders, Laura and Mike. We're very happy to help you out. Ask them specific questions, things you don't understand, and ask for a specific answer. Okay? So again, you are in charge of your own success. You identify which parts of the material are not easy going for you, and you act on it. Make sure that you get that information and be able to do the questions next time around. Okay? So I want to remind you, it's only 15% of the grade. This is for a particular reason. 15 may sound like a lot, it really is not. Okay? The final is almost half of the grade. The final is really where it's all happening. Okay? This exam is really just a warming up exercise, just to get started. So don't be demoralized if it didn't go so well for you. Actually, if it didn't go so well, it tells you which things you have to improve on. So it is more like an opportunity than a penalizing experience. Okay? Yes?
Do we get our midterm back?
Let me go through this list first. Okay? It's actually on the slide. The grades of all the tests will not be curved. Only your cumulative grade will be curved. Your cumulative grade is 2 midterms, 1 final, and the homework together. That is your overall grade of this course. That will be curved. In my opinion, it doesn't make a lot of sense to curve individual exams. A much better measure of your performance is to look at your score. Your score is a metric. It is a number that tells you how well you did. The maximum score is 100. If you have 50%, it means you did half right within the allotted time. That's what it means. Very good indication of your performance. Don't do arithmetic at this stage of the game. It makes no sense. It makes no sense to do that. Did I have an A or a B? It makes no sense. At this stage of the game, the only thing you should be concerned about is, do I understand the material? Okay? That is what you're here for. Worry about this arithmetic just till the very, very end. Okay? Don't compare your performance with other people right now. It is just a waste of energy. Okay? Your exam will be available on the Triple E page on Friday, if everything goes right. Okay? So we have, as you notice, we graded everything on Friday. Very hard work. Okay? Lots of educators have to play that. Everything is done manually with a very small team of people. Pizza stains all over your exams, you will see. Okay? They are now currently in the copy center. They're all being scanned and reproduced, and you will see the PDF version in your mailbox. Okay, so you have your own PDF version of your exam. This will take a couple of days. This is not within my control. It's now in the copy centers. Okay, you can contest your score if there is a genuine grading error. Okay, don't come to me, please, with all kinds of arguments about why you should have more partial credit. Okay? That's not really the purpose of contesting your score. Okay? We have given partial credit, and we stuck to a very specific recipe for that, and we think we've done a great job. If your answer is correct, but you didn't get the points, you're entitled to get extra points. But if your answer is not correct, and somewhere in the margins you've written something that may be right, a little bit of imagination, we cannot give you extra points for that. Okay? So, because if you guys do that, then basically I'll be out of my job. I'll spend all my time on that. It's impossible. That's also not the purpose. I think we graded very fairly. Okay, so the grading errors will be considered till this is a Friday, the 9th of November. So that means you get your exam back on Friday, no later than Friday, this Friday. And then you have 1 week time to talk to me. Talk to me. Send me an email. Okay? If you have simple questions, send me an email. I can do things very quick by email. If you have specific questions, you come to my office hours, so you can make it, or you make an appointment. The TAs are happy to discuss answers with you, but they cannot give you partial credit. Only I can do that. Okay? All right, let me quickly look at one question on the exam. It's about the can of Coca-Cola. This question, surprisingly, went not so well. Okay, lots of people were probably confused by this question. Let me go through it and just put these elements in place. Okay? It says a doctor advises the patient not to consume more than this. Okay, so this is 85 grams. Okay, so I'm just quickly converting it in my head. This is 8.5 times 10 to the minus 2 kilograms, and it's 85 grams. Okay, this patient should not consume more than 85 grams of sugar a day. Okay? Now, in one of these cans, there are 12 ounces of, this is 12 ounces, okay, and it contains sugar at this concentration. So this is a volume. This is a volume, and this is a concentration, or a density, as you can see. This is gram over liter, this is mass over volume. And this is a density, and this is a volume. How many of these cans can this patient have? All right? And the conversion here of ounces to milliliters is shown as well. So, what do we need to calculate here? Well, what I need to calculate is, in the end, how many cans can the patient consume? What is that dependent on? Depending on how much sugar is in there. Okay? 85 grams is the max. So what I need to know is how many grams of sugar are in one can. Okay? I need to know how much sugar is in this can. It's a very simple thing. If your doctor tells you you cannot eat so much sugar a day, and you see all this Coca-Cola food, you want to know how much sugar is in there. How many grams of sugar is in one of these cans? Right? How do you calculate that? So that's a mass. Mass is volume times density. Do I have that information? Yes. There is the density, there is your volume. That volume is not in milliliters or liters or whatever, but the conversion is right there. So what I do is this. Mass equals, this is the density, which I quickly convert from liters to milliliters. Okay? That's a factor of 1,000. If you can do that quickly in your head, you can just write it out, because the difference between a milliliter and a liter is a factor of 1,000. Okay? So 0.110 grams per milliliter times the volume. And the volume is right here between parentheses. I want the answer in milliliters, so I use this conversion right here. 12 ounces, that's the volume, times this conversion factor. You see that ounces will cross out, I get my answer in milliliter. So if you execute this one here, you have your volume in milliliter, times this, milliliter, you get an answer in grams, 39 grams. 39 grams in one of these cans. That you are almost right here at the answer. This multiplication here of 1, 2, 3 numbers is basically the whole thing. Right? How many cans can you have? Okay, well, I have a maximum of 85. This is 39. So how many 39s are sitting at 85? 2.2. I can have 2.2 cans. That's it. That's the calculation. Okay, another issue is naming compounds. Naming compounds is something you can literally learn. It's a method. If you stick to the method, you will be fine. I saw a wide variety of very interesting creative answers. I'm going to give you several. Some people say this is sulfur fluoride. It's almost right, but not quite. This is hexafluoride. Okay? Sulfur hexafluoride. Oh, this is a nice one. I remember in one of the lectures I say, be careful. About 20% of you guys are going to do this one wrong. Okay? Because you will say sulfide, and it is sulfur trioxide. And again, I wouldn't say 20%, but about 15% of the folks did exactly this. Okay? So, pay attention to this. Because even people, that's actually very interestingly, they put a 2 minus here, as if I forgot to put a 2 minus there. They put a 2 minus here, and I said, oh, it's sulfide. This is sulfur trioxide. It's a neutral compound. Okay, this one. Some folks said dicesium carbonate. This is an ionic compound. You never use this indicator. Okay, this prefix. It is cesium carbonate. Ionic compounds do absolutely not have prefixes indicating the number of atoms. How about this one? A lot of folks said this, copper 1 selenide. But selenide is in the same family as oxide. Right? It's in the same column. So this is 2 minus. That means that the copper is 2. It has a charge 2 plus. Oxidation state 2. This one. Now, what does this mean, guys? It's dissolved, and this is an H. What does it mean? It's an acid. Still. Okay, a fraction of folks still call this hydrogen nitride. Okay, don't do it again. Okay, this is nitrous acid. And this one, lastly, this is almost the same kind of situation as in this one, copper selenide. People call this barium, actually not the same situation as here. They think this is a type 2 metal. Barium is not. Barium is 2 plus type 1. Okay? It's in the second column, and those are type 1 metals. You never specify the oxidation state of type 1 metal. So this is not barium 2 chloride, but just barium chloride. Okay. Keep these things in mind, keep practicing, and then we'll see by the time the final comes along, you'll be in good shape. We have to move on, okay? We're going to chapter 3. So we did already a quite big chunk of the material so far, and we're hopping into the next set of topics. Okay, so what is this about? In chemistry, we deal with a lot of atoms. I mean, a material that you can hold in your hand, a solution, the sugar in your coffee, it's not one molecule. Okay? It's many. So instead of talking just about one thing, we talk about collections of atoms, like collections of people. But the problem is that these collections are rather large. Okay, so just to give you an idea, this is one person. You can easily think of this one person, just conceptualize it. There he is, one guy. And then we can even conceptualize this situation here as counting with about 300 million people. Even though 300 million people is a huge number, for some reason our brain kind of understands that number. Okay, we understand 300, it's about this. So we kind of conceptualize it. Now, if you look at ions and molecules and atoms, the numbers are rather staggering. Okay? So this is one ionic pair. We can easily grasp this is just one sodium and one chlorine ion. They're together. Nothing is wrong with it. Easy to conceptualize. But what if you have one of these little chunks? One little grain of salt, kitchen salt, already has 1 times 10 to the 19 ionic pairs in it. 10 to the 19 is a staggering number. Okay? That's huge. This number here fades compared to how many ions are in there. Okay? Our mind cannot comprehend the magnitude of this number. You can try, but you don't, because you don't have a frame of reference. Okay? You're kind of lost with this number. And consequently, it's hard to do calculations and manipulations with these numbers. So it makes a lot of sense for chemists, and also for you, that you are an aspiring chemist. You don't know it yet, but you will. To have a different way of treating these large numbers. And you have heard this number, and that's the mole. Right? What is it? It's a number. I can feel the excitement. Okay? It is a number. That's it. That's all you have to know. Who is laughing so hard? Others laughing. You think it's funny, the number. You think it's a funny number?
My chemistry teacher in high school made me memorize this number, like my name. So.
Oh, really? Oh, that's great. So how many digits do you know?
Huh?
You know, how many digits do you know? 4 digits or 5, 6, 8? So this number is big, right? It's big. It's 6.022 times 10 to the 23rd. And that's a very, very big number. But it is a number. I just want you to understand it's a number, like any other number is. It has no units right here at the moment. Okay? So it's a number like 12 is a number, or 6 is a number, or 223 is a number. This is just a different number. It's a quantity of things. So how is it defined? Where does the number come from? Well, it's defined, again, through our best friend, the carbon atom. Definition is as follows. 12 grams of carbon-12, that is the isotope of carbon. Okay? Isotope 12 of carbon. Carbon-12. If you have 12 grams of only these atoms, then the definition says you have 1 mole. Okay? So if you stick to the definition, if you say that this is the definition, you can count what you have. And it turns out that this definition stipulates that you have this many. Right? So if I tell you this quantity here, 12 grams of carbon-12, that is your metric. That is your new unit. Okay, you say, give it here. I'll count how many of these things. Oh, I count this many atoms in there. And that's it. That's the definition. Nothing mysterious about it. Just the definition. You have to define it somewhere, so this is a pretty good definition, like any. Okay? So, again, I just want to re-emphasize it is a number. People mix this up. People think a mole is something mysterious. No, just a number. Like a dozen is a number. You have to refer to comparison probably, but it's really true. Okay? You can have 12 atoms, or you can have this many atoms. In one case, you call it a dozen. In another case, you call it a mole. Now, it is surprising that if I give you a question and I replace every word mole with the word dozen, you have no problem solving the question. And if I put the word mole for dozen, you are completely confused. Or at least a whole bunch of people are confused. Because you think a mole is hard to understand, but it's not. It's just a number, like dozen is a number. Okay? So in case you are confused by a question and the word mole is like slapping you in the face, just secretly replace mole by the word dozen, and suddenly you think, oh, I just have to multiply two numbers. Okay, so let's look at a couple of consequences here. All right, so if I have 1 mole of carbon C12, okay, 1 mole of it, well, then I have 12 grams. Right? That's basically the definition. 1 mole of carbon C12 equals 12 grams, because 12 grams of carbon C12 is 1 mole. That's my definition. All right? So, the mass of carbon 12 is 12 AMU, 12 atomic mass units. Okay, that's another definition. That's how atomic mass units are defined. So 1 mole times this, I just substituted this here for that, equals 12. It's the same line. But from this, I can just bring this guy to that side and conclude the following. 1 mole equals 1 gram per atomic mass unit. Atomic mass unit is a unit of mass. Gram is a unit of mass. So, in fact, it's dimensionless. Okay? It doesn't relate to a physical unit. It is just a quantity. Now, this is a very useful kind of conversion, if you want, or relationship, because I can do the following. I can take another element, let's say aluminum. Okay? 1 mole times the mass of aluminum. Okay, so let's say 1 mole of aluminum atoms. The mass of aluminum atoms is supposed to go here. What is the mass of aluminum atoms? Well, in AMU I know what it is. It's right here. 26.98. That follows from the periodic table. The average mass of aluminum atoms is right here. That is the number in the periodic table. Okay? If I multiply that by 1 mole, look, 1 mole is this. So I put that right here. I see AMU will cross out, and I get an answer in grams. In other words, this is 26.98 grams. All right, so what does the line say? The line says if I have 1 mole of an atom, I get my mass expressed in grams. Okay? The average mass of the atom is now expressed in grams as opposed to AMU. So every time you take 1 mole of these atoms, that means a whole bunch of them together, then the mass of that will be equal to the molar mass of that element. That is AMU replaced by grams. Okay, so let's have a look at the periodic table. This is what we just did. We have an element. We take exactly 1 mole of that element. It turns out its mass is equal to its atomic mass in grams. And it holds for every other element. Potassium, you take 1 mole of it, you get this mass, which is the number in the periodic table, which is in the periodic table it says AMU. But if you take 1 mole of these elements, you get that number in grams. Zinc, same thing. You take 1 mole of zinc atoms, you get this mass here, the number in the periodic table, are now expressed in grams. And it holds for any other element, doesn't matter which one. Okay? That's great, because now I can just take 1 mole of all these elements and I know how much they weigh expressed in grams, what the mass is expressed in grams. Okay, so let's do an exercise here. Let's take this block of titanium, a small little cube of titanium, and let's assume that this little tiny cube is 3 grams. Okay? And I'm going to ask myself the question, okay, I have here 3 grams of titanium. How many titanium atoms are in there? That's what I want to know. How many titanium atoms are in there? So I have to do a conversion. I have something in grams. I want something in number of atoms. How do we do that conversion? Well, one way to do that is this. I have grams. I know how much 1 mole of titanium is, namely this number here in grams. Okay? I can make a conversion factor. 1 mole of titanium equals this many grams. And I can use this as a unit factor, okay, conversion factor in my calculation. So what I do, I start with listing this number in grams. I'm going to synthesize out of here a conversion factor. I want to go to quantity, number. Mole is a quantity. So I put mole on top and this at the bottom. I do this multiplication. You see, gram will strike out. And I get now the number of moles of titanium that are in 3 grams. Okay? This is it. 0.0626 moles of titanium. So how many atoms are there in this cube? Well, this many. Okay? This is a quantity. This many. But the quantity is expressed in moles. And I want it in real numbers now. So how do you do that? Well, this is in moles. I just multiply it by what the mole is. Just like if I said you have this many dozen titanium atoms, you would multiply by 12. So I multiply just by 6.022 times 10 to the 23rd. Okay? I take that number, multiply it by what the mole is. That is a mole. This number is a mole. And then I get the number of atoms. 3.7 times 10 to the 22 atoms. Again, this number is rather staggering. That's why we typically don't really bother about really calculating the amount of atoms, and we stay on the level of the moles. Because those numbers are much easier to work with. That's the purpose of a mole. To make calculations easier and more manageable. Okay, 2 quick examples. A sample of CO2 has 1.4 times 10 to the 3rd moles of oxygen atoms. Now the question is, how many moles of CO2 molecules are present? Okay. So what is the question about? Well, this question is about this. What is given is how many oxygen atoms you have, not how many molecules of CO2 you have. Okay? I know how many oxygen atoms I have, but from it I can determine how many CO2 I have. So it's a relation. It's the same as saying you have 2 eyes. You all have 2 eyes. So if in this room there are 600 eyes, how many people are there? 300. So each person has 2 eyes. It's the same here. Each molecule has 2 oxygens. Right? So for each molecule there are 2 oxygen atoms. So what I want to do is just take that number and divide that by 2. Then I get this number, and that means I have this many CO2 molecules. And this is another situation where the different word can confuse you. If I say molecule and atoms, you tend to think that this is going to be a very complicated calculation. But if I say eyes and people, nobody has an issue. So mathematically, this is a joke. Right? But just conceptually, you have to give these things meaning. Don't be afraid of the number of atoms or how many atoms there are in a certain molecule. It's just accounting. It's just like 2 eyes on a person is accounting. The sooner you can convince yourself that this is all straightforward, the faster you will get to the answer. Okay, how many moles of H atoms are present in this molecule if I have 2.88 moles of it? Okay, again, 2.88 moles is a quantity of molecules. All right? What I want to know is how many H atoms I have, the quantity of H atoms. So what I see here, I have a molecule. It contains C's and H's. It contains 6 H's. So for each one molecule, I have 6 hydrogens. So how many hydrogens do I have? Well, I take this number, which is a number, a quantity, and I multiply that by 6, 17.3 moles of H atoms. That's it. I just have to multiply this number by 6, and that's the answer. Very easy, it seems. And these simple exercises are just for you to get used to the words molecules, atoms, and don't be afraid of doing these calculations. Yes?
What about carbon in the first
Well, I mean, you know, that's the same as saying if I tell you that there's 600 eyes in the audience, how many people are there? Okay, then your question would be, but hold on a second, how many noses are there? Right? I said, well, there's 300 noses, right? Because each molecule has one carbon. So that means there's just the same number of carbons as there are molecules. The question was about oxygen and how many molecules you have. Eyes and people. But of course, people have also a nose. Actually, people have many more things. They have 2 arms, they have 2 legs, they have all kinds of things. This CO2 has only carbons and oxygen. Okay, now, what holds for atoms also holds for molecules as a whole. What does that mean? That means the following. I can determine not only how much or what the mass is of 1 mole of an atom, I can also determine what is the mass of 1 mole of a particular molecule. Right? So, for instance, let's take this one. C2H6O. That's ethanol. If I have 1 mole of ethanol, what would its mass be? How do you calculate that? Well, what you have to do is you have to see what's in it. 1 molecule of ethanol has 2 carbons, 6 hydrogens, and 1 oxygen. Right? If I have 1 mole of ethanol, that means I have 1 times 2 moles of carbon, 6 moles of hydrogen, and 1 mole of oxygen. So that's what I have to calculate. Here we go. The mass of 2 moles of carbon equals 2 times the mass of 1 mole, which is this, 12 grams. 6 moles of hydrogen is 6 times the mass of 1 mole of hydrogen, which is 1.00 grams. And 1 mole of oxygen is just the mass of oxygen, 1 mole of it, which is 16 grams, or 15.999. Okay, so what you have to do is you have to do these multiplications and then add them up. Okay, the answer is 46.07. That is the molar mass of ethanol. So that means if you have 1 mole of ethanol, a certain quantity of ethanol, you will have, if you put this thing on your balance, you will say this is 46.07 grams. Okay? So we say 46.07 is the molar mass of ethanol. Okay, so we can do it for any other molecule, right? So let's do it for aspirin. Aspirin is a cool molecule. Makes you feel good if you have pain. It's a very, well, it's not very simple, but it's a small molecule, relatively speaking. Okay? Here is the line structure, your favorite way of drawing molecules from now on. And here is the chemical formula. The chemical formula is in this regard very important if you want to calculate the molar mass. Okay? It has 9 carbons, 8 hydrogens, and 4 oxygens in it. So what I want to do here, the first step I want to do, even before worrying about this question here, I want to know what is the molar mass of this compound. So what I do is this again, 9 moles of carbon, that means 9 times the mass of 1 mole of carbon. That's 9 times 12.011. That's this number right here. 8 moles of hydrogen, 8 times the molar mass of hydrogen, which is 1.008. Do the multiplication, you find this. And then 4 moles of oxygen, because there's a 4 here. That means that 4 is right there. 4 moles of oxygen, 4 times the molar mass of oxygen, which is about 16. They get 64 is contributed by the oxygen. You put a line here and you add it on. 1 mole of aspirin is 180.60. So, if I had 1 mole of it, this would be its mass. Let's look at this number here. I want to know how many moles are in this mass. This mass is much smaller than this mass. Why do I say that? Because if you calculate how many moles it is definitely much smaller than 1 mole. Okay? So if your answer is going to be larger than a mole, you did something wrong. I need to find an answer for 50 milligrams of aspirin, and I know it's going to be a number much smaller than 1 if I express it in number of moles. So what do? I write down again the quantity, which is 50 milligrams, expressed in grams, 0.050 gram. Why do I do that? Well, because this is defined in grams, not in milligrams, so I rewrite this in terms of grams. Then, the conversion. Where do you want to go to? To moles. Where do you want to move away from? I want to move away from grams. So I put gram at the bottom, moles on top, like this. This gram will cross out, and this calculation gives me a number expressed in moles. This is my unit factor, like we did with conversions all the way. Okay? 2.8 times 10 to the minus 4. That is the answer. So this question is converting a quantity expressed in a mass unit, grams, milligrams, into a quantity unit, which is moles. And you can use this unit factor to do that. Okay, vitamin C, another very cool molecule. Here it is. Vitamin C is nothing but ascorbic acid. And here's the structure. Again, a relatively small molecule with quite some majestic implications for human health. If you don't have this thing, if you don't ingest it, your body can't make it. Right? So you have to ingest it through veggies and fruits, and you are actually boosting your immune system. This molecule has 6 carbons, 8 hydrogens, and 6 oxygens. So knowing this, those subscripts tell me exactly what the molar mass is going to be. Because I'm going to do 6 times the molar mass of carbon, 8 times the molar mass of hydrogen, and 6 times the molar mass of oxygen. Okay, there it is. 6 times 12, 8 times 1.008, 6 times 16, and the total is going to be 176.12. That is the molar mass of vitamin C. Okay, that's it. What is the question here? How many oxygen atoms are there in 5.3 micrograms of vitamin C? This is a number expressed in grams. So I have something in grams, micrograms, okay? A mass unit. I have to convert it into a quantity unit. So it's a conversion problem. I'm going to need this. I'm going to need this as a conversion factor. They want the answer in oxygen atoms, the number of atoms, not the number of moles. So I have to do an extra conversion and multiply in the end with what a mole is. So let's get that one by one. What I do is I'm going to write this right there, okay? Expressed in grams. 5.3 times 10 to the minus 6 grams, because a micro is 10 to the minus 6. I want to convert this from gram to number of moles first. That means I take this thing here, put mole on top, and this thing at the bottom. Grams will cross out. And I get my number now expressed in terms of number of moles. I find 3.0 times 10 to the minus 8 moles of ascorbic acid or vitamin C. This is 2 significant figures, so I have 2 significant figures right here. Is this the final answer? No, it's not. Because they want to have it in number of oxygen atoms. Okay, not in moles of the molecule. There's 2 things I have to do. First, I have to determine how many oxygen atoms there are for each molecule. That's 6. And then I have to convert that to number and multiplying that with the mole number. So let's do that. This is the number of moles of vitamin C molecules. This is what 1 mole is. So I do this multiplication and get the total number of molecules. 1.8 times 10 to the 16 molecules of vitamin C. Again, replace this not by the mole number, but by the word dozen. And what you would do automatically, without even thinking, you would say, oh, you have this many dozen? Okay, that's just like this number times 12. Same here, just multiplying with the mole number. Or Avogadro's constant, whatever you would like to call it. Okay, this is the number of molecules. Each molecule has 6 oxygens, so the number of oxygen atoms is 6 times this. Right? This number times 6 is going to give me my number of oxygen atoms. 1.1 times 10 to the 17 oxygen atoms. Make sure you really understand this and you're very comfortable with a calculation like this. Okay? And discriminate number of molecules from number of atoms in the molecule. A molecule can have multiple atoms in it. But that number is going to be bigger than that. Okay. Another one. How many moles of lead 4 chloride are present in this many grams of it? Another conversion from grams to moles. A one-step conversion. If you know the molar mass of lead chloride, you can directly calculate how many moles there are in this mass. What do? The molar mass, if you calculate it first, go to the periodic table. 1 lead atom. This is the molar mass of lead. Okay, 4 times the molar mass of chlorine. That is the molar mass of chlorine. 4 times that. We add this whole thing up. 349.0 grams per mole. Okay? For each mole, you have 349 grams. This is my conversion factor. I'm going to write down this number. Okay? Well, this is another way to say it. The number of moles is nothing but the mass divided by the molar mass. This is another way to memorize the same trick. Basically, you take your mass, which is this number, you multiply by a conversion factor where always this number appears at the bottom. And on top, it's 1 mole. In other words, it's mass divided by molar mass. That's a quick way to remember this. Okay? So, 5,440 grams divided by that number equals 15.6. That's the number of moles. So this formula here is exactly the same calculation we did on the previous slide. You take your mass in gram, you multiply by unit factor, mole on top, molar mass at the bottom. This is 1, so you smoosh it together, you get mass over molar mass. Right? That's what this is. It is the same calculation, smooshed together in one expression. Number of moles equals mass over molar mass. Okay. Another one, very quick. Another sample, iron. And this is carbon monoxide. It's found to contain, what's happening? This is a complex, okay? This is a complex of iron and carbon monoxide. It contains this many grams of oxygen atoms. How many grams of carbon atoms are present? This is interesting. I have to convert a number of oxygen to the number of carbon atoms. Okay? Express your answer scientific notation. So I know the number of oxygen. What is the number of carbon atoms? Well, it's 1 to 1, actually. Okay? The number of oxygen atoms is basically the gram divided by the molar mass. That is a quantity. So 1.94 times 10 to the minus 5 grams, that is the mass quantity, divided by the molar mass gives me the number of moles. Okay? 1.21 times 10 to the minus 6 moles. So what I did, I took the formula from the last slide, N and BA, number of moles, equals mass over molar mass. Mass over molar mass gives me a quantity expressed in moles. This is how many oxygen I have, and that is the same as the carbon molecules. Okay? In other words, I have exactly the same number here for carbon. 1.21 times 10 to the minus 6. The only thing you have to do here is convert a mass quantity into a mole quantity. That's it. And you do that by this expression. What time is it? Oh, look at this. I can do one step more, because what they ask is not how many atoms you have, but what is the mass of those atoms. So once you have the number of atoms, you multiply it by the molar mass. Okay? So what I find is this many moles, this is the molar mass. The number of moles times the molar mass gives you the mass. Okay? So let me reiterate it again. This is number of carbon atoms. Okay? Number of moles. This is what 1 mole weighs. What the mass is of 1 mole. So let's say 2 dozen eggs, okay? 1 dozen weighs 5 grams. So you multiply these two numbers. Exactly the same here. You have a number in moles, molar mass, you multiply the two, you get your answer in grams. Okie dokie, that's it, and I'll see you on Wednesday.